Hello there, denizens of the deep. We're now continuing in 4.4. This is part 2 of section 4.4. And now we're getting into a concept of linear dependence and linear independence. So let's just motivate it a little bit. So if you have a set of vectors, v1, v2, up to vk, just a bunch of vectors, a finite set of vectors, and they're part of some vector space v. Notice I always use capital V for the vector space and small v's, but bolded for the vectors themselves. So the vector equation C1v1 plus C2v2 plus dot 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 plus CKvk equals 0 always will have a trivial solution, meaning where C1, C2, CK all equals 0. That's always going to be, because if I make all the coefficients 0, no matter what the vectors are, the total is going to be 0. By the way, notice that over here we have a bold 0. Here we have a not bold 0. The difference is this is 0, the number, and this is 0, the vector. This is the 0 vector, and this is the scalar number 0. Now, sometimes there are going to be non-trivial solutions, meaning where they're not all equal to 0. And let's just look at an example of that. Let's look at let's look at this one. S is the set 1, 3, 1, 1, 0, 1, 2, and 1, 0, negative 5. So these are 3 vectors in R3. And we already did the work in example 1 to see that V1, which is 1, 3, 1, can be written as 3 times V2 plus V3. That means that the vector equation C1, V1, C2, V2, C3, V3 equals 0 does have non-trivial solutions. In fact, it's going to be 1 times V1 minus 3 times V2 minus 1 times V3. But I don't, for some reason, I wasn't able to make a subscript. Sorry about that. Anyway, C1 is 1, C2 is negative 3, and C3 is negative 3. Now, when it is possible to find a non-trivial solution, we say that our set is linearly dependent. So when it's possible to find a non-trivial solution, then the set of vectors is called linearly dependent. And if it would be impossible to find a non-trivial solution, then the set would be linearly independent. So let's just get the official definition right here. So the official definition, if you have a set of vectors in a vector space, it's called linearly independent, where it's impossible to find scalars to make a linear combination of 0, unless of course the scalars are all 0. And if there are non-trivial solutions, I mean, if it is possible to find non-zero numbers to make this sucker equal 0, this linear combination, then it's called linearly dependent. So if I can make a linear combination with non-zero coefficients, it's dependent. If it's impossible to do that, and I can only do it with all 0 coefficients, then it's independent. Here are some examples. So here's some examples of linearly dependent sets. So you have the set, let's just get them all right here. So S is equal to the set 1, 2, 2, 4. Well, negative 2 times 1, 2 plus 1 times 2, 4 is the 0 vector. So you see that I was able to find non-zero numbers to make a linear combination equal to 0. Here we have 1, 0, 0, 1 and negative 2, 5. But if I do 2 times the first vector minus 5 times the second vector plus 1 times the last vector, again, I get the 0 vector. So again, these are non-trivial, these are non-zero coefficients. And S, if S is the set 0, 0 and 1, 2, then I have 1 times 0, 0 plus 0 times 1, 2 equals 0, 0. So this is a non-trivial solution because one of the coefficients is 1, even though the other coefficient is 0, but one of the coefficients is 1 right here, and hence it's linearly dependent. Okay, that was loads of fun. Now let's figure out. Let's say you have a bunch of vectors, and you want to find, is it dependent? Is it independent? Like which one is it? What is it? So there's a way we could, very simple way we could sort of test it, verify it, and we're using knowledge that we've established already. I love the way this linear algebra, how it kind of builds on itself, meaning that the concepts that we've learned with matrices, we're applying them to vectors. And that's the way linear algebra is. It kind of builds on itself. It's kind of awesome. So S is the set of vectors 1, 2, 3, 0, 1, 2, and negative 2, 0, 1. Okay, and we want to see, is this dependent or is it independent? Which one is it? So what we're going to do is that, let's look at the equation C1, V1, C2, V2, C3, V3 equals 0. If we find that the only solutions are 0, 0, 0, then it's independent. If we can find, if there are other solutions, then it's dependent. Well, here's what we're going to do. We're going to write, instead of just writing V1, I'm actually going to write 1, 2, 3. And instead of writing V2, I'm going to write 0, 1, 2. So here we go. C1, that's the coefficient we're looking for, times 1, 2, 3, plus C2 times 0, 1, 2, plus C3, that's the last coefficient, times the last vector, negative 2, 0, 1. That will equal, we're setting that equal to the 0, 0, 0. So we want to see, what do we get when that happens? So first I'm going to just distribute. I'm going to, well, actually I'm going to regroup everything. In the first component, we have 1 times C1. We don't have any C2 because there's a 0 there. And we have minus negative 2 times C3. So you see in the first component, C1 minus 2 times C3. That's the first component right there. In the second component, we have 2C1 plus C2 by the same idea, by the same argument. And the last component is going to be 3C1, 2C2, and C3. And we're setting these equal to 0, 0, 0. Guess what? This is going to give us a system of linear equations. It's going to give us three equations with 3 variables. And the 3 equations are going to be C1 minus 2C3 equals 0, because I'm setting the first component. That corresponds to the first component. And I'm setting the first component equal to 0, so that's my top equation. Now I'm setting the second component equal to 0. That gives my middle equation, 2C1 plus C2 equals 0. And I'm setting the third component equal to 0. So this is my third equation. By the way, if you're very sharp, you might have noticed that the first vector here was 1, 2, 3, and the coefficients going down the first column are 1, 2, 3. The second vector was 0, 1, 2. The coefficients going down the second column are 0, 1, 2. Now you don't see the O there because it's nothing there. And the coefficients in the third the components of the third vector are going to match up with the coefficients of the third column, negative 2, 0, 1. And why does that happen? Well, it's kind of obvious. I mean, just look at the process. When you go through the process, you can see why that's happening. Because, well, for example, well, it's the first vector has all the C1s go to the 1, 2, 3. That's why the C1 column is going to be 1, 2, 3 ultimately, and so on and so forth. You can figure this out. If you work, when you actually do these by hand, you kind of see why it works. Anyway, so here's the augmented matrix, and we're looking at the augmented matrix, and it looks like this. I'm just taking the coefficients and the thing, and we get that right there. So that tells us that C1 equals 0, C2 equals 0, and C3 equals 0. So this is, drumroll please, linearly independent. Now I just wanted to show you the steps of this, how we did this this Gauss-Jordan elimination. So I have it right here. So we started with 1, 2, 3, 0, 2, negative 2, 0, 1. I took negative 2 times row 1 plus row 2, and that became my new row 2. And also, I did negative 3 times row 1 plus row 3, and that became my new row 3. Now, I'm often, hesitant to do 2 steps at once because it could mess things up. But these 2 steps are totally independent of each other. That's why I did 2 at once. Anyway, I wind up getting, so my row 1 stays the same, 1, 0, -2, but my row 2 becomes 014, and my row 3 becomes 025 when I do these 2 operations. Now I'm going to take -2 times row 2 plus row 3. That's going to be my new row 3. Again, what I'm trying to do is I'm trying to eliminate, I'm trying to eliminate that 2 right there. So I have all zeros, and I get this sucker right here. Now, the truth is, I could really, if all we want to do is figure out if we're dependent or independent, I really could stop right down here. I really could stop right down here, because once I have a triangular matrix, then I know that I'm going to have the determinant of this matrix is just going to be 1 times 1 times -3, which, if you notice, is not 0. And we know that when a determinant is non-zero, that means you can get it down to unique solutions. You can get it down to a 1-1-1 situation. Just from this point right here, I know victory is ours. Anyway, let's continue on the steps. -3 times R3 becomes my new R3. And then finally, I add 2 R3s to R1. That's the new R1. I subtract 4 R3s from R2. And there I go. I have my beautiful identity matrix. And that's how that works. Very nice, very simple, very elegant, very beautiful. Here we have a summary of the steps that we just did. So I'll let you read this. You can pause the video and read it for as long as you want. Okay, let's do some examples of testing for linear independence. So we're looking at 3 vectors in P2. P2 is the quadratics, the second degree or less polynomials. So 1 plus x minus 2x squared, 2 plus 5x minus x squared, and then x plus x squared. So this becomes C1 times the first polynomial plus C2 times the second polynomial plus C3 times the third polynomial. And that should, and we're setting that equal to the 0 polynomial. And now I'm distributing and I'm gathering together the like terms. These are the pure constants right here. These guys here are the coefficients of x. So I take C1 times x, C2 times 5x, and C3 times 1x. So that's why I have C1, 5, C2. That's where the 5 came from over here, and C3. And these are the coefficients of x squared, and we're setting them equal to the 0 polynomial. And now we want to see, is there a we want to see what's the story with the solution here. So let's take a look. So we got here, moving right along. So we have this system of equations because we're setting each thing. By the way, again, notice that I have here 1, 1, -2, and that's 1, 1, -2. You see that? And here I have, in the second polynomial, I have 2, 5, -1, 2, 5, -1. In the third polynomial, I have a 0 constant plus a 1x and 1x squared, 0, 1, 1. So that's, because if you think about a polynomial, these are kind of like, I'm going to say analogous or very similar to an R3 vector. You see what I'm saying? I mean, the coefficients of a quadratic is very similar to an R3 vector, the components of an R3 vector. So anyways, here's the augmented matrix we get. And that means, now, when we get the augmented matrix, if you notice, we wind up with a row of zeros. Now, row of zeros means that this does not have a 0 determinant, obviously. And now, when I say determinant, how can I possibly have the determinant of a non-square matrix? So I'm just talking about the coefficient part, because the truth is I'm just looking at the coefficient part of it. So since the coefficients do not have is going to be a 0 determinant, then that tells me that our matrix is going to not have a unique solution. In fact, it's going to have infinite solutions. It's going to have infinite solutions. So let's now, what are the steps? What are the steps of this? Let's just go through the steps of this Gaussian elimination. So here is my original coefficient matrix, and I'm adding -1 R1 plus R2. That becomes a new R2. 2R1 plus R3 becomes my new R3, and now I have this. And my goal, of course, my strategy was I wanted these zeros down here. Well, if you notice, row 2 and row 3 are the same. Well, the truth is, once I see that, I can really stop. I can stop at this point, because once that happens, it means that this is going to wind up having a zero determinant, and it's all going to be messed up. But let's just continue. I'm subtracting row 2 from row 3. That becomes my new row 3, and I get a row of zeros, which is, again, you know, once you get a row of zeros like that, we're doomed. And and then just to put it into that Gauss, whatever, row echelon form, whatever. So I divide everything here by 3, and I get this. But the truth is, I already saw, once I did that first step and I saw this 3, 1, 3, once I saw the same row repeated twice, or that row 2 and row 3 were equal to each other, I knew that, you know, a situation was hopeless, and and this is going to have a zero determinant. And that's something we all know. Now, as I said, a row of zeros implies there are infinite solutions. Well, I'd settle for just one right now. So what we're going to do is that, because of the third over here, I'm going to set C3 equal to 3. Now, this means that C2 plus 1/3 C3 equals 0. So I bring this over to the other side, and I get C2 is equal to negative 1/3 of 3, which is -1. So that's why we got that right there. And once I know that C2 is -1, so that tells me that if I bring the negative, this becomes 2 times C2, so this becomes -2. Bring it over to the other side, I get C1 equals -2, which is +2, and that's what I got right there. So 2 times the first polynomial plus -1 times the second polynomial plus 3 times the third polynomial equals 0. And I would like you to multiply out these polynomials, distribute them, and you'll see that you indeed get 0. I'm going to let you do that by yourself. Okay, here is another example of testing for linear independence. And boy, I feel like it's like Independence Day. I get it. So we have 3 vectors, which are in the form of 2 by 2 matrices, and I want to find coefficients to multiply each vector. I'm not calling them, even though these are matrices, I'm not calling them matrices, I'm calling them vectors, because we're viewing them now as vectors, and set it equal to the zero vector. Even though this is the 0 matrix, I'm calling it the 0 vector. See how cool and awesome I am. So anyways, when you multiply this all out, you wind up getting a system of 4 equations. And I love the way they say this: use Gaussian elimination to show the system has only the trivial solution, which means S is linearly independent. So let's just do that. Let's do it right now. Let's see how the Gaussian elimination is going to look. So here is the Gaussian elimination. This is I made a matrix now now, by the way, I didn't bother with a column of zeros, because when you move the rows around, the zeros are just going to stay 0. So like, it's a waste of ink. So I'm doing actually 3 steps, because they're all kind of independent of each other. I'm taking -2 row 2 plus row 1 becomes my new row 1. I'm taking negative row 2 plus row 4 becomes my new row 4, and 1/2 of row 3 is going to become my new row 3. And you see, all these 3 steps are independent of each other. And I wind up getting 0, 0, 3, 1, 1, 0, 0, 0, 1, 1, and 0, 1, 0. Now I'm switching row 1 and row 2, so I got this sucker right here. So now it's looking in the form I need. And I'm going to, instead of dividing by 3 and getting fractions, I'm just going to switch row 2 and row 4. So now I have 1, 0, 0, 0, 1, 0, 0, 1, 1, and 0, 3, 1. We're looking good here, looking good. And finally, well, not finally, but the next thing I'm going to do is I'm going to take -2 row 3 plus row 3 is going to become a new row 3. Oh, sorry, -3 row 2. In other words, I want to use this 1 over here to get rid of that 3. And -3 times row 2 plus row 4 is going to become a new row 4. So I'm using row 2 to change row 3 and to change row 4. and I wind up having, so I'm starting from this point, doing these two operations, and I get this, and that, and that. Look at that. Now notice that these two rows are the same, so I'm going to subtract row 3 from row 4 to become a new row 4, and I have this. This is row echelon. Now, before I made a whole speech about, oh, if you have all zeros, it means zeros. Well, that only applies when you had a, when you started with when you're dealing with a square matrix. This is not a square matrix anymore. So this is actually 4 equations with 3 variables. It's a whole different world. And I got my reduced row echelon form. So and I got to go all the way across the board. And this is indeed one. This indeed is going to give us one solution. The one solution, of course, is going to be the first guy equals C1 equals 0, C2 equals 0, and C3 equals 0. That's, because don't forget there's a column of zeros here. Okay, let's go back to the page. So there you go. There you go. So we see here that this only has a trivial solution. So these 3 vectors are linearly independent. And there you go. Next. Here's another one. I'm gonna go through. It's starting to get tedious already, so I'm gonna go through these quickly. This one is just. I just wanted you to see what it looks like when you write your vectors as column vectors rather than write them as rows. But it's really the same thing. So we're looking at the matrices M4, 1, which is basically these column matrices, which are column vectors or whatever you want to call them. I'm not going to go through all the steps of this like I did in the previous ones. I just want to run through it. So you multiply, you find, you take 4 coefficients, multiply each vector by a coefficient, and hopefully get the 0 vector. And that gives you this equation over here. And if you do use Gaussian elimination, and by now you're expert at it because you've seen me do it a whole bunch of times, you will find that it only has the trivial solution, which means you're going to get this in, well, you'll see. So do it. Now this, by the way, is a 4x4. This is 4 equations with 4 variables. And so this will actually be a square matrix, I'm just saying. Anyway, let's moving right on. If a set of vectors is linearly dependent, then by definition, this has a non-trivial solution. Okay. And which leads us to the next thing, a property of linearly dependent sets. So you have a set of vectors, when there's at least 2 vectors. If you don't have 2, what's the point? So it's linearly dependent if and only if at least one of the vectors can be written as a linear combination of the other vectors. That kind of makes, that's like very obvious to me, but we'll go through the proof. So let's see, here's the proof. So first we're going to start, we're going to prove it in one direction, not the band One Direction, but one direction. It's interesting though, there was a band, a very popular band, One Direction, but they all went their separate ways, which is kind of ironic, One Direction. Anyway, C1. So we're gonna assume that C1 V1 blah 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 equals 0. Well, let's bring everything over to the other side. So I have C1 V1 equals -2 C2 V2, -3 C3 V3, negative CK VK. I think I said -2. I meant -C2 V2, -C3 V3, dot dot dot. Now divide everything by C1 because it has to be. Now we don't know. How do you know C1 does not equal 0? Well, I don't know that C1 doesn't equal 0, but it's got to be, it has to be at least one vector that doesn't equal 0. So I'm going to pick that vector. So let's just assume it's C1. It might not be C1, it might be C7, but there's at least one non-zero vector. Divide by that, and I get V1 is equal to -C2 over C1 V2 plus -C3 over C1 V3, all the way down. But notice this is a linear combination of the vectors V2 through VK. So I've shown that if this whole sucker equals 0, I can rewrite this all so it's a linear combination. Similarly, if I do have or conversely, I'm going to say, but it's the same, it's going to be more or less the same thing. If v1 is equal to a linear combination of other vectors, all I got to do is bring the other vectors over. Either brings, well, I was going to bring the other vectors over to the other side, but I see here they brought v1 over to the other side. It doesn't matter. I get negative v1 plus all these other vectors equals 0. So I have, and I know there's at least one non-zero coefficient, which is -1 itself. And that's important. You have to know there's at least one non-zero coefficient. That's the definition. But what I like about this is that now the word dependent kind of makes sense. Because if it's linearly dependent, it means I can write one vector in terms of the other vector. So that one vector kind of depends on the other vectors because that one vector can be constructed by the other vectors. Now, by the way, let's move on. I don't want to get into any by the ways yet. Okay, so we're going to actually, I'm going to say my by the way. Then we're going to stop this video and we'll continue in part 3. But I just want to say that it should be pretty clear that if you could write one vector in terms of all the other ones, you could write any vector in terms of all the other. Whereas once you can write v1 in terms of the other vectors, I could write v2 in terms of the other vectors and v3 in terms of the other vectors, and so on and so forth, just by solving for v1, solving for v2, solving for v3, solving for vk, the same way I did for v1. So kind of, it's kind of interesting like that. So even though the definition is that there's one vector, but really once you have one, it's going to be true of all of them. So let's stop now, and that's the end of part 2, and we'll continue in part 3 later on. But now, where we're going to continue, we're going to continue right here from some more examples from example 12. We're going to continue next time from example 12.